Okay, in this video we're going to wrap up section 1-2, linear equations in one variable. So we're going to talk about the intercepts of the graph in an earlier section. Just in the last section, 1-1. We looked at graphs and we figured out, they could cross the x and y axes in, 1, 2, or no places. We saw some maybe parabola look like this, where we would have one intercept on the y-axis, and we might have two intercepts here on the x-axis. And in the previous section, we mostly looked at that graphically, just looking at the graph and figuring out where those numbers hit. And I did give you a little sneak peek because we had one up here. It was between I think 10 and 8. The exact answer was 9, but it was kind of hard to see from the shape of that parabola. So now we're going to do more of finding those algebraically. Because all the points on the x and y coordinate because all the points on the x-axis have a y-coordinate equal to 0, and all the points on the y-axis have an x-coordinate equal to 0, we can use an algebraic approach to find these x and y axes, or intercepts. So to find these algebraically, to find the x-intercept, you set y equal to 0, and then solve for x. To find the y-intercepts, you set x equal to 0, and solve for y. So here is our equation, y equals 4x plus 1. I'm going to write it here, y equals 4x plus 1. And then again on the right, y equals 4x plus 1. What we're doing is just giving each variable a turn at being 0. So in this one, I'm going to let y equal 0, and then I'm going to solve for this x. And then I'm going to let x equal 0. 4 times x would be 4 times 0. Plus 1, and I'm going to solve for y. So we're giving each variable a turn. So if I solve this one, here is 0, I got this plus 1, I'm going to subtract 1 from each side. So now I have a negative 1 on the left equals 4x, and I divide by 4, and I'm going to get x equals negative 1/4. And then this other equation where I let x equal 0, well here 4 times 0 is 0, so this is simply y equals 1. And this is a nice easy way to sketch a graph of an equation, especially a straight line. I know here on the x-axis I cross at negative 1/4, so maybe that would be right about here. Negative 1/4, I have an x-intercept. And then on the y-axis I cross at 1, that would probably be about up here. And since it's a first power equation, 4x to the first power, I know that it is going to be a straight line. That's not the best straight line, but you get the idea. We find the two x and y, the x and the y intercepts, and we can just connect the dots, and there's our line. In this one, we're going to find the x and y axes also algebraically. I just threw this one in here because it does have some decimals. But I'm going to write it twice. 3y plus 2.5x minus 3.4 is equal to 0. And I'm going to write the same equation, 3y plus 2.5x. I did forget my x over here. Why didn't you tell me? Minus 3.4 equals 0. So I've let now I'm going to let each variable have a turn being equal to 0. So if I let y equal 0, if y equals 0, that wipes out this term. And I'm just left with 2.5x minus 3.4 is equal to 0. And here I'll let x have its turn being equal to 0. If I do that, 2.5 times 0, that wipes out this term. So what I'm left with here is 3y minus 3.4 is equal to 0. Now I just solve each of those equations for the one variable that's left. So for this, I would add 3.4 to each side, and I would have 2.5x equals 3.4. And then I would divide. 2.5 divided by 3.4 is 0.7352. So x, and since we are rounding this off, that doesn't look like it's ever going to end. 7353 will round it off to 0.7353, and it's not equal to that, it's approximately equal to that. And then we got to finish off this equation here for the y variable, 3y. I'm going to add 3.4 to each side here, so I get my 3.4. And then I want to divide by 3. 3.4 divided by 3 is 1.13 repeating. So y equals 1.133, and we'll put the little bar on there for repeating. As long as we got the bar, we can use the equal sign. If I wanted to round it off, I would have to use the approximately equal to, and then we could just round that off to 4 spots, like we did on the other one. And there's our, x and y intercepts for this equation. And it is x to the first power, so that would be a straight line. All right, I think we got one more example before the practice problems. Example 5 is just sort of a real-life application to this stuff we're talking about. It says here, female participants in athletic programs. The number y, this is measured in millions, of female participants in high school athletic programs in the United States from the years 1999 to 2008 can be approximated by this linear model. Y equals 0.042t plus 2.73 for t values, and t is going to be time in years, for t values between -1 and 8. And this data does come right from the National Federation of State High School Associations. This is a real model that some mathematician or scientist, crunched a bunch of numbers and worked it all out and came up with this relationship between time and the number of female participants in athletic programs. So this is real-world data that you can get right from that National Federation of High School Associations. So where t equals 0 represents the year 2000. Time 0 is 2000. We would go to -1, and that would take us back to 1999. For part A, they want us to find algebraically the y-intercept of the graph of the linear model shown in the figure. And B, assuming that this linear pattern continues, find the year in which there will be 3.36 million female participants. So let's see here for part A. For part A, they're asking us to find the y-intercept. To find the y-intercept, we set x equal to 0. Or in this case, it's going to be t for time. So we want to find the y-intercept. We're going to let the other variable equal 0. So the model says 0.042t, and we're replacing that t with a 0, plus 2.73. And this is an easy one to figure out. 0 times this wipes that term out. So we have our y-intercept already. Y equals 2.73. If we looked at the graph, we can verify that, that's got to be in the ballpark. We are between 2.5 and 3.0. That does fit in there, but that's not a number we can find exactly just by looking at the graph. Okay, let's see here, part B. Assuming that this linear pattern does continue, if this, model does accurately predict the future, assuming this continues, find the year in which there will be 3.36 million female participants. So what they're asking us to do is, t is time. We want to find the time it's going to take for us to have an output value, a y value, of 3.36 million female participants. So for part B, they're giving us the y value that we want. That's 3.36. And they're asking us what value of t makes that happen. So we're going to have our 0.042t plus 2.73. This is the model that some scientist or mathematician come up with. We want to find out what value of t is going to give us that many millions of female participants in the athletic programs. So the first thing I'm going to do here, I'm going to subtract that 2.73 from either side. So I'm going to have my 0.42t. 3.36 minus that is 0.63. And then I'm going to divide by the number in front of t to get t alone. So divide by that 0.042. That cancels out, and we get t equals that 0.63 divided by 0.042 turns out to be a nice even 15. So it's going to take 15 years for that to happen from the start of this, and they're saying, in what year, find the year which this occurs. Remember, when this starts, we are in year 0 is the year 2000. So we want this to happen in 2015. 2015, if these predictions hold true. Right now, when I'm making this video, it is 2013. So we'll have to wait a couple years, find the data, and see if this model, is accurately predicting what's going on. Okay, I think that's it for the examples. Time, yeah, for the practice problems. These are some pretty straightforward equations here. It says find the x and y intercepts of the graphs algebraically. And, these should come out, most of them are going to be nice whole numbers. You might get a fraction, though, a pretty decent fraction. So pause the video, try the problems, start it back up, and see if you got them right. All right, let's see here for this one. You can write the equation twice, 16 minus 3x. Y equals 16 minus 3x. And we're going to give each variable a term being 0. So if I set y equal to 0, then 0 is equal to 16 minus 3x. I could add 3x to each side, so I'll have 3x equals 16, and divide by 3. X equals 16 thirds. That is our x-intercept. And then on the alternate hand, we can set x equal to 0. So y equals 16 minus 3 times 0. Well, 3 times 0 is 0. That's gone. So we have our y-intercept. Y is equal to 16. Okay, let's try 86. We have 4x minus 5y equals 12. First, I'll let x equal 0. If I let x equal 0, that term gets wiped out. And we're left with minus 5y equals 12. So we would divide by negative 5. Y equals negative 12 fifths. And then we'll let y be equal to 0. So, this minus 5 times 0 is 0, and that term is wiped out. And we're left with 4x equals 12. Divide by 4, x equals 3. There is our x-intercept, and there's our y-intercept. This, if you, in class, we would do this in the on the T99 graphing calculators. Remember, I'm trying to get you as comfortable with those as possible leading up to the SAT test. So if you're watching this video from home from missing class, if you weren't in when we did this, find some time, a study hall before or after school. Come and, we will go over this problem together.